Good, thank you. I should apologise if Gregor was listening on the net. This presentation had been delivered into the system before I got his modifications. So this is the second last version.
Okay, thanks.
Okay. Yeah, Dave Cameron. My current role is that I do a lot of time things in this Oslo not related to chemical engineering. But 1 day a week I'm still allowed to be a chemical engineer. And the stuff I'm doing is around interoperability for engineering information. And the work on that is built in a context where the Norwegian oil and gas industry is facing challenges in that we're going to have to become the Norwegian energy renewables industry. And as part of that, they're still developing oil fields up in Norway. And there's a field which used to be called NOACA, which was understandable in English, and it's now called Yggdrasil, which is completely unpronounceable by non-Norwegians and is a name for Norwegian mythology. But it's a quite complex field where you've got, originally it was going to be built by 2 operators with an unmanned platform, which is the one in the circle, which is the one we've been doing a lot of work about. And because you had a collaboration between 2 oil companies and 2 engineering companies, they devoted money to trying to work out how you do interoperability. And they priced in demonstration deliverables to show that they can move from paper-based delivery to data-based delivery for things like process and instrumentation diagrams, process design, process flow diagrams, electrical design, single line diagrams, and equipment specifications. And the ones in yellow are things that paper and chemical engineers have got something to do. And the idea is to move from document-centric to data-centric engineering. And there's a concept called aspect systems, which actually came into the chemical engineering community through Wilco Marquardt and the people in Aachen with the AutoCAD, the ontology for process engineering back in 2010. So, a little bit of what DEXPI is. DEXPI is animated slides. DEXPI is at the moment, voluntary and somewhat financed effort to create neutral standards for engineering. And it's quite a large number of people. It's a community who are willing at the moment. They're currently working on becoming a German non-profit organisation to get a bit more commitment to exercises. And so, the DEXPI Plus working group was given a mandate that you can go out and have a look at a DEXPI standard, and that standard defines a way of trying to represent information on piping and instrumentation diagrams. Now, the next question was, okay, we can do piping and instrumentation diagrams, and we're currently, with the Norwegian industry, stress testing that standard by trying to send piping instrumentation diagrams around that field development I showed you. The next question was, what about the other diagrams? The process flow diagrams and the safety diagrams and the block flow diagrams, which are documenting early phase design. What is the linkage of those 2 PIDs? And can we create some sort of vendor neutral model for these sort of drawings? Now, state-of-the-art practice for a process flow diagram is you get a drawing tool and you draw objects. There isn't usually a connection to any smartness behind these objects. And we believe that there should be some sort of object behind that. Now, in parallel to this thinking in DEXPI, we've been approaching the task which we've got from Equinor and Arca Solutions to say, please give us PFDs as digital information. So we've been doing some work on that, and then Equinor pointed to us and pointed us at DEXPI and said, let's create a standard together on this. So, a question which is next way. So what you see, these are the typical examples of the sort of things you have on process flow diagrams. Now, there is a gap in the standards on how we describe things. Because what does a symbol on a BFD or process flow diagram actually represent? And if you go into the various standards, there's lots and lots of different answers. And most of them are saying, well, that's actually a distillation column. Or, well, no, it isn't. It's actually a system that's performing a process. So what you've done is you've used a symbol that says distillation column and said that I'm actually trying to model here a distillation process, which I'll eventually go and buy some sort of equipment to realise that process. And so what you're going to do is you want to be able to have process requirements, process constraints, and build up a model of functional systems. In early phase design, you're not so much concerned about what you're building, you're concerned about what you're trying to do in the plant. And so we're looking at not looking at a distillation column, we're looking at a system for distillation. Or here we're not looking at a pump, which is actually two pumps in parallel. We're looking at a system that you need to do to pump this fluid. Okay, probably a bit laborious over on that. And it's rather interesting that standards have been able to test this stuff because Arthur D. Little, 100 years ago, invented the concept of unit operation, which in some ways completely revolutionised the discipline of chemical engineering. Turned it from being industrial chemistry, where people built bits of equipment, into the discipline we know today of chemical engineering. And so what we have here is that in DEXPI, piping and instrumentation diagrams, you're dealing with things, plant items, type by noun, a valve, a pipe, a pump, a heat exchanger. It's a physical object, it's a thing, and you're asking there about how large, how heavy, constructed of what, and which product are you putting into. Up in process design, we're looking at something which is a process step, and you type that by verb. Compressing, pumping, distilling, separating, regulating flow. So when you see a valve in a PFD, you're thinking, I need something to regulate flow. You're not thinking, I have a valve here. And there you're asking questions about how far, how much, how fast, how efficient, how near to completion, and how pure. Process requirements. And so we have at the moment, and this is taken from both system engineering, this V diagram, where you have functional requirements, you know, how fast, how much, how well the process is going to behave. And then you have equipment requirements, which are about actually, will this piece of equipment actually tolerate the pressure I have? What material am I made of? Will it corrode? Questions. And what you'll see in operation is the equipment functional requirements will result in maintenance things about how well the bit of equipment is behaving. But then when you want to do process optimization, you'll back up again, trying to get access to process functional requirements. Now, the trouble at the moment is all the standards we have talk about things. And what you see in engineering information systems is all that information you need to do process simulation is rolled down onto a long list of parameters related to a thing. So you've lost all the connection up to the process functional requirements. So DEXPI Plus tries to bring this standards landscape in that direction so that we can actually document process design in a good way. If you like three-dimensional diagrams, which I don't, this could be an interesting way to look at it. You're saying, okay, we're looking at some system and we look at it in three ways. First, we think about what it's going to do. That's conceptual design. Then you say, okay, to achieve this functional design, we actually have to build something. And that's the structure, the piping instrumentation diagram, your specification sheets, and you've got DEXPI and SheFOS covering that area. And then the thing tying it all together is the behaviour. And that's where K-Bergen comes in. Because it's about simulation and thermodynamic properties. And those things you want to show on a PFD through your speed tables. So today's design approach is that you get a pile of digital paper sent over from the company, the recommended practices, the standards, the API standards you're going to use. You then structure a manual configuration of a model for a PFD, which you put into your simulation platform. And then you generate out a set of specifications. You then manually or using macros on Excel, put that into the constraints that you put on your simulation. And then you run lots and lots and lots and lots of cases. Those cases give you a set of results, which then give you simulation cases, which you put into another Excel spreadsheet and then put onto the stream tables in your PFD and send it to the operator. And that eventually gives you the design, which is an even huge, bigger pile of paper. What we want to do with our digital engineering is to be able to pass around objects that contain engineering information. We want to be able to get rid of Excel, and we want to create standard ways of talking about cases, results, specifications, and constraints, so that this work process will be made less Excel-based and substantially more efficient. So, I've taken a use case from the Cape Open monitoring interface specification, which is about archival of multiple runs of a flowsheet. Because that's exactly the exercise what we want to do in design, where we start building our main process systems, building down through the system until we get to a point where we need to be able to actually specify equipment, we create our PID. And what we want to do here is that you want to be able to take that design, that PFD design, and run many, many cases and get the right cases and create the design window you need to actually then specify your equipment. So to be able to use that simulation in a sensible way and get that information automatically and not using private Excel-based interface simulators would be a nice thing. So we've designed DEXPI Plus as a library of process steps. Now, the lovely thing about chemical engineering also is there aren't that many process steps in chemical engineering. We'll show you a little bit more. And what we do is we, again, it's not rocket science. We use an approach where you have a block with ports, where you have the ability to put details in. So things like I'm going to do separation and packing or on trays. And then you have sources and sinks. And then you can connect these ports either by energy flows of different types, information flows, or streams. Looks a lot like the Cape Open one. It's not accidental because we basically stole it from Cape Open. And that stream contains a material state, which is information you have in the stream table. And you have different types of streams because you define a project-specific material template, which says, for my hydrocarbons, I'm going to have this set of components and use these methods. So that gives you the structure for the material state. So here's the idea of the material template. The material state object is the thing we want to get data out of simulators put it into to produce stream tables. And I think this offers potential for data exchange with simulators. So what we've developed in the standard is a hierarchy of process steps. Now, obviously, people will come to us and say, yes, but you need another 5 or 10 process steps to make our life as biochemical engineers better. But what we have is generating flow, mixing, splitting, storing, supplying, exchanging thermal energy, separating of all sorts of different processes. And what we do is that we have also a hierarchy of process steps. So early in design, you say, I need to separate, I need to heat, I need to do something. And at this stage, I don't care how I'm doing it. As the design proceeds, you're then getting down to the level of unit operations and component systems, where you're also saying, yeah, and I'm going to compress using centrifugal motion. And then that has process implications for the rest of the flow sheet. So you actually have to track that decision on how at this stage of the process design. So then we have a library of separation by distillation, transporting and piping, compressing by centrifugal motion, as an example. So what we have here is the ability to build up a structured model of a process you have. You then, and also you can associate variables with those specific processes. And what we're doing here is creating a structure that you can refer to by making specifications. And what we often see in standards is that the standard will say a valve is going to have a parameter called maximum allowable working pressure or minimum ambient temperature. Now that's useful, but what you're doing by specifying that in the standard is you're making that model very fragile, because every one of those type of qualified specifications you make is going to actually break the model when you want to make a new type of that specification. So what we've done in DEXPI Plus is said there's an ambient temperature for a block, there's a temperature for a block, there's a pressure for a block. And then you as a user can then create many, many different statements about that pressure, qualified by what mode or range or provenance you have on that variable. And that way we can map across to GFOS, because GFOS really likes those sort of lower limit, upper limits, average type parameters. But this makes us more flexible and enables you to create a structure file which doesn't contain any data at all. And then in parallel to that, lots and lots of case files which actually contain the numbers. So a little bit of example to motivate. Here's a well-known demonstration process called the Tennessee Eastman process. And we were able to model that process flow diagram. It's a fairly effective process flow diagram because the Tennessee Eastman people deliberately didn't actually put in any controllers, because the whole idea was to design control structure. And so we then turned that into a model where we draw up a library. In this case, we use UML as a prototyping tool for the exercise. We need to develop some better tool support for this, but this demonstrates the data model. And what you see is that you build up blocks with ports, connections between those blocks. The important point is a connection with no length. A connection says, I go from one system into the other system, and I'm responsible for handing over something there. And the topology naturally resembles what comes there. We've also tried it out using a tool called Automation ML, which is a automation industry standard for structuring data and exchanging data, and it works very, very elegantly. So, okay, quickly, using DEXPI process files to store design cases. Well, as I said before, we create a data set containing a structure, how things are tied together, and then you, as an engineer, can prepare data sets that contain specifications that point into that structure, saying things that are going to be necessary. So you have parameter values, and you can specify values of the material states in ports. Simulator can then write data sets that contain the behavior of the process. Again, referring into the naming structure you've got in the DEXPI Plus structure. Now, to do that, we've got some challenges about interaction with the simulator. Structure, there's no way of implementing, configuring, auto-configurating the simulator based on a structure written in any standard. So you've got to manually map across to there. Same at the moment with specifications. Cape Open doesn't write numbers back to simulators. And so, however, the flowsheet monitoring interface is capable of sending us results back at this stage. And by doing a little bit of reading around the monitoring interface, I found this diagram showing a set of objects which map pretty nicely to the DEXPI Plus objects. I had a discussion with Michelle on my misunderstanding of what the role of material template was. So I think actually it's not quite fair to say that it's not in thermodynamics 1.1. But we have the ability to define these things. And we map it this way and say that, okay, the process step corresponds to a unit operation in Cape Open. Ports correspond to ports. And your streams, energy flows, and information flows map one-to-one to these objects in Cape Open. Now, what sort of procedure do we then need to do to extract information from simulators? Well, okay, you've got a project, you've got your favourite simulator, and you're basically not going to choose that. That's been supplied by either your customer or your company procedures. So the first thing you need to do is to map the process step types in DEXPI to unit operations in the process simulator, and map the support structures. to the library unit operation ports in the process simulator. So this is going to be a cross-reference table of type to type and port to port, hopefully at the library level, not the individual level. So you can reuse that information. And then you can map the block parameters with the exposed parameters from each unit operation. And then that's at the preliminary work, trying to do it at the simulator level. And then at the project level, you can then map the DEXPI material template with your Cape Open material template or the thermodynamic spec in the simulator. And you can map process step identifiers with unit operation identifiers. Again, if necessary, you then can have to map special parameter identifiers and stream the energy interpolation flow identifiers. And then the material objects with material state objects. Now, with that mapping set up, you're then in a situation where you'll be able to ask the monitoring interface to supply back the information you need for the technical files. So this is a thought experiment at this point. We're doing a little bit of work around with DWSIM to try to show how this can work in practice. And what I wanted to do here is just present this as a thought experiment and as a challenge. I believe it's also an opportunity to get Cape Open and DEXPI to work together a bit more and to also advance how we document process requirements around these sort of objects. Another opportunity is if we can get the electrical people, the instrumentation people, and other disciplines thinking the same way, we can cross-connect objects with these different types. Okay, thank you. That's my contact details. A lot of this depends on a man called Harold Waller, who's professor.
Thank you, David.